Across fields and forests, plants quietly build starch from captured sunlight. In every grain, long glucose chains fold into dense, waiting stores. Rice kernels, corn seeds, wheat berries, and potato tubers carry this pale reserve. For animals and people, starch promises energy, but not in its first form. Its sweetness is locked inside spirals and branches too large for taste. Water can swell starch granules, and heat can soften their compact bodies. Yet the hidden glucose remains tied together, bead after bead after bead. Long before factories, living mouths, and sprouting seeds knew another answer. Malt awakens with enzymes, loosening grain starch for the young shoot's first growth. Fungi in damp soil also learn to enter this starchy treasure. Their thread-like bodies secrete quiet tools into crumbs, roots, fallen fruit, and seeds. Among those tools, glucoamylase became one of nature's most patient finishers. It works at chain ends, freeing glucose one small piece at a time. Where other amylases make fragments, glucoamylase keeps walking towards simple sugar. The human story began with starch turning sweet under mysterious, controlled conditions. In 1811, Gottlieb Kirchhoff showed acid could convert starch into sugar. His observation helped early industry, but it was chemistry with a harsh hand. A gentler clue arrived in Paris, carried by Malt and careful glassware. In 1833, Anselme Payen and Jean-François Persoz extracted diastase from sprouting barley. They had captured an enzyme mixture years before the word enzyme existed. Diastase made starch lose its paste and become a soluble, fermentable sweetness. For biology, it opened a doorway into invisible molecular labor. Throughout the 19th century, brewers and bakers trusted such hidden workers daily. But glucoamylase itself still remained unnamed within the broader amylase crowd. Another path was unfolding in Japan, inside the living culture of koji. Koji molds had long helped rice, soybeans, and grains become fragrant food. Their aromas came with enzymes that opened starch for yeasts and people. In the 1890s, Jokichi Takamine brought fungal amylases into modern industry. His fungal diastase showed molds could supply powerful preparations for changing starch. It was not pure glucoamylase, but it pointed toward fungal abundance. Decades later, researchers began separating starch enzymes with far greater care. Japanese work by Junichi Fukumoto and Yoshio Tsujisaka became especially decisive. In the 1950s, they described fungal enzymes that released glucose directly from starch. Rhizopus molds and later Aspergillus niger revealed glucoamylases of unusual usefulness. Aspergillus niger, a dark common mold, became central to scientific study. Researchers learned fungal enzymes could finish what malt enzymes often left behind. The enzyme gained names: glucoamylase, amyloglucosidase, and eventually, glucoamylase. Each name circled the same talent, making glucose patiently from starch. By mid-century, starch refining was ready for a gentler transformation. Acid conversion could be forceful, uneven, and hard on metal vessels. Enzymes offered selectivity, working like small hands rather than fire. Glucoamylase joined alpha-amylase in a new, practical understanding of starch. First, long starch was opened into shorter chains that could move freely. Then glucoamylase patiently trimmed those chains into glucose, end by end. This partnership reshaped sweetener production through precision instead of brute force. Under the microscope, glucoamylase is not a blade or crushing mill. It is more like a pocket shaped for the chain's delicate end. A starch strand docks, held for a moment by subtle attractions. The enzyme guides water into the right place for a bond's release. One glucose slips free, and the enzyme lets the shortened chain go. Then it catches another end, repeating the calm, precise gesture again. Even branch points can be approached, though more slowly and carefully. The result is ordinary glucose, the same small sugar cells recognize. In bakeries, glucoamylase helps dough release fermentable sweetness for waiting yeast. In brewing and distilling, it helps starch become sugars microbes can use. In rice wines and traditional ferments, its cultural heritage feels especially close. In starch refining, it supports syrups, dextrose, and many familiar food ingredients. In animal feed, it can help unlock grain energy more gently. In plant-based processing, it turns agricultural starch into useful fermentation building blocks. Those building blocks can become organic acids, amino acids, and biochemicals. Some journeys lead beyond food, toward materials made from renewable carbon. A corn kernel can become sweetness, fuel, or the start of compostable plastic. Behind that transformation stands an enzyme once hidden in mold and malt. Glucoamylase reminds us that industry can borrow wisdom from decomposition. The forest floor has always been a laboratory without walls or patents. Its fungal threads recycle fallen starch into life's circulating sugars. Our future may depend on listening closely to such small chemistries. Less heat, fewer harsh steps, and more biological precision can matter. In glucoamylase, history finds a quiet tool for greener making. Behind Enzymes Bio is a team of scientists who love this quiet biology. We gather enzymes from across the world so researchers and businesses can order from one home. Nature's technology for a greener tomorrow. See more at enzymes.bio.